In this unit, we begin our look at electromagnetic induction, which is all about using a magnetic field to create a current in a wire. Now, we know we can do the opposite. We know we can take a current-carrying wire and get a magnetic field. But can a magnetic field actually create a current? And the answer is yes, but only if the magnetic field is changing. If an unchanging magnetic field is there, we don't get a current. But if we take the magnet and move it through a coil of wire, then we can get a current in the wire. A current produced by a changing magnetic field is called an induced current. And so this diagram kind of shows what's happening. If you take a magnet and move it through a coil like that, then we get a current in a certain direction through that coil. If we move the magnet the other way, then the current reverses direction. But if we hold the magnet stationary, no current flows through the wire. Now, we actually use the term electromotive force to describe this. Electromotive force is an old term that was used before people understood what was happening with electricity. Electromotive force was what an object had if it could create a current. Now we know currents flow because there is an electric potential difference between 2 points. We measure that potential difference in volts, so we refer to potential difference as voltage. So when you see the term EMF, you should think voltage. It's simply an old school term for that. Now, because a current is induced in a wire, that wire is acting like it's hooked up to a voltage source. So we say that a changing magnetic field induces an electromotive force, which creates the current in the wire. Now, in order to understand what we mean by a changing magnetic field, we're going to go to this concept of flux. Flux refers to the amount of magnetic field lines passing through an area, and that's what this picture shows. These blue lines are magnetic field lines, and that tan little square is an area that they're moving through. Now, flux only refers to the perpendicular component of the magnetic field. So if the magnetic field was exactly parallel to this thing, there is no flux. If it's exactly perpendicular, that's maximum flux. And at this angle, then we actually have to include that angle in our calculations. And you'll notice that angle is measured to the normal, or the line perpendicular to that surface, and so that's the cosine of the angle to get the perpendicular component. So the magnetic flux is given symbol phi sub b, and it's equal to the area times the magnetic field times the cosine of the angle between them. And it has its units. The units are Webers. A Weber is a Tesla meter squared. Now, once we know magnetic flux, then we can actually calculate the induced EMF using Faraday's law. Faraday's law relates the rate of change of flux to an induced EMF. So remember, that flux has to change in order to get an electromotive force. If there is a constant flux, if the magnet's stationary, the coils are stationary, if there's no relative motion between them, then we get no current. So, Faraday's law simply says if the flux through a loop of wire changes by an amount, delta phi b, over a brief time, delta t, then the EMF during that change is given by EMF equals the change in flux divided by the change in time. Now that's for a single loop of wire. If there's multiple loops of wire, all we have to do is multiply this by n. Okay, so one loop of wire, that's good. If there's multiple loops that the magnetic field is cutting through, then we multiply that by n. Now that tells us the size of the electromotive force, but it does not actually tell us the direction. And to get the direction of the electromotive force, we use Lenz's law. Lenz's law is pretty straightforward. Lenz's law just says that the current that's induced will create a magnetic field that opposes the change in flux that induced it. Okay, so maybe that's not simple. But essentially, all it says is the induced current maintains a constant magnetic field, or it tries to. So if the magnetic field decreases, then the induced current will try to increase that magnetic field. If the magnetic field increases, then the induced current is going to try to oppose that magnetic field. And I have an example here to take a look at. So, in which direction is the current induced in the loops for the following scenarios? So these are magnetic fields, right? This is a magnetic field coming out of the page. This is magnetic field going into the page. Here we have magnets moving through loops. So on part A, we have pulling the loop to the right here. Now, if you think about this, these magnetic field lines are up out of the page, but because this is coming out of that magnetic field, those are being reduced, which means the current that's induced in this wire is going to try to keep more magnetic field lines coming up out of the page. So it's going to induce a magnetic field in this direction. And in order for that to happen, using the right-hand rule, we know that our current has to create field lines coming out of the page, so that means the current has to be flowing counterclockwise around that loop. Here the loop shrinks, and so again the number of magnetic field lines going through this loop is going to decrease, but these field lines are into the page, so we want to increase the number of magnetic field lines going into the page, and in order to do that we're going to get a clockwise current around this loop, so that's going to end up clockwise. Here we have a magnetic north pole. Remember, magnetic field lines emanate from the north, moving towards the loop into the page, which means we're getting more magnetic field lines this way. Those are increasing, so our current is going to try to oppose those, which means it's going to try to create magnetic field lines the other way, and that means counterclockwise current. Then we have a north magnetic pole moving towards the loop in the plane of the page. Here, we're not going to get anything. Okay? Because these are in the same plane and the magnetic field lines are not perpendicular to the field, nothing happens. There is going to be no current induced. Now E is a little bit different. We have magnetic field lines going to the left, and we're going to rotate this loop around this way, and so initially there is no flux in that loop because they're parallel to each other. They're all in the same plane. But as this loop rotates in, magnetic field lines are going to be going through that loop. So there is going to be a change in flux, and it's going to be increasing to the left, which means this thing is going to try to create a magnetic field inside it to the right. And in order for that to happen, the current needs to flow in that loop counterclockwise. Okay. Whoops, one too many C's. So Lenz's law just tells us, let's try to maintain the status quo. If we have lots of magnetic field, we're going to try to keep lots of magnetic field. If we're decreasing our amount of, if we're increasing our magnetic field, we're going to try to decrease it. Okay. So not terribly complicated, but you do have to think about it a little bit.